Welcome back. Okay, so I'm gonna go through some of the slides, and we're gonna talk about over here, first here, and then Australia in a more general sense with relationship to this region. Because I watched some videos, let's call them lectures, that I thought I would share. So let's do that. So I just took screenshots from this lecture. It was about Peter Betts presents Cretaceous evolution of Zealandia dictated by congested evolution or subduction. And it relates to the Hikarangi Plateau. So we've been talking about oceanic plateaus. If you haven't seen my last few episodes, one of them has the music too loud, so sorry if you don't like the music, and certainly especially exacerbating that you don't like the music when I have it too loud. But alas, I've been talking about oceanic plateaus, so again, just a real quick synopsis of my interpretation of them as part of the Earth's expansion process, where the Earth does not function under plate tectonics, but instead expanded due to undercurrents that were emitted from the Earth at the mantle puncture hole, which occurred in Pakistan, which then flowed out in all directions below the crust and filled up pressure until the Earth physically broke apart, and other details with like surface currents occurring and water being released, flooding the Earth, and radiometric dating being only valid for relative ages without accounting for details like the Earth expanding. So these currents flow out in all directions and collide, and then at those points they basically prevent the flow of one another, which then builds up mounds of material at those points, which in these instances lead to oceanic plateaus. Let's see if I can find it. Let's see if I can find it. I should probably have gotten ready. Here we go. So, Ontong Java Plateau, directly above Solomon Islands, was forming here where an undercurrent was coming this way, colliding with another current coming this way. And then there's another current over here kind of holding a boundary. And that led to buildup of material, which was probably more so over here until this space opened. Like this space opened. This Papua New Guinea was actually down this way with Solomon Islands until this space started to open. And Ontong Java Plateau formed, according to science. Like I'm basing this all off of evidence I've found in technical sources. Obviously interpreting it through my own lens, but the evidence is there. Ontong Java Plateau formed, which is here, this formed with the Manihiki Plateau, these oceanic plateaus, which formed with the Hikarangi Plateau, which is over here in this region, as one unit which is called the Ontong Java Nui hypothesis, that they were together. So it's not like proven to a point where it's just like absorbed into the models, but that is the like running hypothesis. It's pretty much like agreed upon from what I can tell by those involved in the research, including this one that we're going to look at. And I think he presents alternatives, and it kind of says it could be this, it could be that, but we pretty much think it's that one. So Hikarangi Plateau is down here, right abutting Chatham Rise, which we talked about in the last episode a little bit, and previously in the one with a lot of loud music. Here's the Ontong Java Nui Plateau, Ontong Java Plateau, Manihiki, and Hikarangi, which essentially ran into, I guess, according to the interpretation, about, mind you, this is a plate tectonics framework, ran into Chatham Rise. All pieces in place to evolve the present configuration of Zealandia by about 80 million years. So 120 they were together, 95 to 80 they extension. Congested subduction. Oops, let's go back. Gotta go the other way. This one I found pretty interesting because this, I think, well, the next image. Collision, this is the collision, I believe, an onset of extension, or maybe the onset of extension is here. Evolution is consistent with what would be expected if collision triggered the margin to collapse and reconfigure. So this collision of this Hikarangi Plateau with the margin is hypothesized to have triggered the collapse and reconfiguration of this area, where like this was over here, the opening of the Tasman Sea, where they were together, and then a plateau moves in here, oceanic plateau, which then triggers the reconfiguration of the region. So if we look at this one, there's a period of collision between North Island and Hikarangi Plateau, and then subduction rollback, back arc extension in southern Zealandia. So North Island of New Zealand, North Island, so it's like colliding with the North Island, and then it's colliding with Chatham Plateau Rise here a little later. Notice the time though. 60, 65 KT boundary time. Anyone who doesn't know, that's when the Earth rapidly expanded. It began to rapidly expand. The pressure below the crust was building and beginning to like fracture the crust, but at 65 million, rapid expansion was initiated. Probably associated in part with this, like this was one of the elements of what was going on that allowed for that to happen. I wouldn't say it was this alone, but so collision along the North Island, present day. Suture advance and continuous crustal shortening in the late Cretaceous. Let me see what I wrote. Quote, we think that the collision of the Hikarangi Plateau was the major trigger of the opening of the Tasman Sea. End quote. Hikarangi Plateau collision with North Island. Okay, so I just was literally, I wrote this. Suture advance and continuous crustal shortening in late Cretaceous, which is about the KT boundary. So there's this collision occurring at the late Cretaceous. Okay, subduction, rollback, and crustal extension and overriding plate away from the collision zone. Sinistral motion on the western Wishbone wishbone ridge to accommodate different differential trench motion. I'm not sure what to make of that. I don't remember exactly what he was talking about. Dynamic models, so this one, I believe, is under the premise that they were, I guess it's after they separated. This one's, they were together 120, separated by, or began to separate in the 115 to 95 range. And the Hikarangi Plateau, according to this, was far away. I would beg to differ, so to speak, because the Earth was expanding. We'll get into some reasons why. I would say it more so went like this way. Basically down this way. And went in there. So let's just look at that real quick. Here's Fiji. Here's Fiji. And then here's this region. Right here, in this region, is this big old blob of magnetic anomaly. This is a magnetic anomaly map that I have basically proven is maps and traces current flows that occurred during the Earth's expansion process by, for instance, here, like current flows, like they even have a bend that they bend around. Current flows. We can look over here on the western region of North America as well. Down here, they're flowing here. Current flows are occurring, and then they fill the pressure under the continents and break them apart, and then they flow out into the space between and form the oceans. Ocean beds, which, once that happens, becomes much more laminar and like regular. Western Pacific aside, because this was forming while the Earth was expanding, while the pressure was building. This was forming physically underneath North America and under Australia, and probably even under some portion of Asia, maybe. Like this right here, this ammonite shape was over here. Papua New Guinea was like over here somewhere. But then it just got moved by the currents shoving it once it's broke apart enough. And currents started to collide over in this location and swirl. And possibly like shortcut across that way. There's something interesting here. That I'm just thinking Ontong Java Plateau is over here. Maybe it contributed to bringing currents over there, or maybe it contributed to cutting it apart. Also, like there's a jet stream that goes this way, but down this way, there's this like flame shape that then has this flow down here that goes into New Zealand. This here is this here down into New Zealand, right there. It's actually in here where that nucleus is here. So it goes down that way. Pushes up a mound on the side of it over here, which is over here. And I'm thinking, mind you, this is, let's go back. This like flame structure is over here. This location right here on the boundary of South America. I know it might be kind of hard to see, so over here before the expansion occurs in the like this region of the Pacific is formed. It's much more localized, but it's like a focal point where energy is flowing to, so it starts to like produce a actual outward pressure that leads to all the structure here that we see, where like right there has these structures out from it and like a leg down, so it's kind of like a snow angel. And it also has jet streams out this way that become like a trident and do all sorts of things in North America. But this portion, this flame, ends up going down the coastline and catching into the boundary of South America, like here, 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 especially here, and just drilling in with its pressure and like changing the angle of the continents, like adjusting the earth to be in an equilibrium by this current coming down this way. It comes from like right there down this way to there, which is why it's especially there. So this is sending an energy down the boundary of South America and into South America underneath it, running into other resistances and leading to these structures over here that are really most visible in this stretch. I don't know why I won't like focus. Definitely is more like normal looking than it is there. So I was thinking, like, while it's doing that, which if it's got this current going down this way and it catches there, right there, like if we follow this over this way, it looks like it's there too, and there, and there. Where does this go? There, there, there. Maybe across this way. Don't really see it over here. But maybe it's taking this Ontong Java Nui plateau that's generally forming from like from over here to over here when they were much closer before this region even opened yet. The continents were physically conjoined. There was no Caribbean Sea. It was just closed. And the Ontong Java Nui was more here. It took the Hikarangi plateau and physically moved it down here to around here. But over here is related to over here, so it deposits, like even though it's against South America, it deposits it in this nook here. So that's kind of my thoughts on the what's really going on with this. Wow, it just kind of opens the Tasman Sea and spaces everything apart so that they're in this configuration they are today. Where one's here, one's here, one's here, even though they're all joined together. This one looks like it's in one of the videos I talked about it having a base that goes over this way along this line here. So if we just use that as like a pivot point to follow like its relationship to where it goes, which is this one right here, goes across, but then it kind of bends down and then goes over here to right there. So it's got a relationship with this area, which on the map is here. This structure is related to this. Maybe to this. Maybe this is related to. What is this? I don't know what those islands are. I think they're islands. They look like islands. They're just blurry. I don't think it's like lag. I don't think it's my computer, maybe. I guess it might be. Maybe I'll close this. Let's just call that Philippines, Australia, save. It's really laggy. Wow. My internet's not working. Crap. I don't think it matters too much. Unfortunately, my internet is not working. So we'll have to be limited to what I have on my computer, but we can just go to back to this. So then conclusions from this, he also talked about like the geological record of New Zealand is super complex because of the dynamic evolution caused by congesting the Gondwana margin. What's congesting it? It's very strange that there's congestion from a plate tectonic standpoint. Like if you think in terms of pressures, there's this, according to plate tectonics, there's still this huge ocean, and yet the margin is being congested. Like it doesn't make sense. It makes much more sense if there are like continental segments adjacent to one another and a lot of like pressures flowing into them. Then there's congestion, like actual congestion. Like if there's a huge road that has thousands of lanes, what they're saying, like what plate tectonics suggests, is that some reason all the cars chose one road, one lane, and are congested in that area when they have all the space to be in. Like it's kind of like stars, like as they get near each other, they have field like magnets that can like push apart from one another, and they're just like too close, and they create a balance. I know that's not like from a gravitational standpoint, but just in terms of their fields interacting, they can create balance between them. But if there's like other magnetic systems pushing in on them, then they're going to be forced together to a point where they get closer and closer and then attach. So it doesn't really make sense that there is this concept to me of congestion at the Gondwana margin when there's this huge ocean. I know we're thinking, well, that doesn't have any meaning because plate tectonics is driven by the convection in the mantle. Whatever exactly reasoning we can come up with for there being like this congestion, I guess because the plate is moving that way. But like ultimately it would reach a balance. Like it wouldn't just be like an engine roaring. Okay, current models are not geodynamically consistent, which I would say is the case for all of plate tectonics, like for those reasons. Like things tend towards equilibrium. They don't tend towards just like continuously slow processes that don't care about equilibrium. They literally don't care about equilibrium. They just keep going. Things tend towards equilibrium. So does the Earth. That's not how it would be. Can explain the evolution with collision of the Hikurangi Plateau with the North Island. So it appears, based on what he's saying, that there is a step where it collides with the North Island. The South Island and Northlands record a Cretaceous evolution dominated by rollback-driven extension in the overriding plate. Some kind of effect of the collision, this material, this mass, gets shoved into New Zealand, and it responds by having this like rollback and probably even breaking away from Australia, like a chunk breaking off of Australia that it becomes New Zealand or Zealandia, whatever exactly. Like, because of the collision, it actually fractures crust further in. Imagine you got like a cracker and you grab the cracker and you bend the cracker and it breaks. It doesn't like break right at your finger though. It breaks within where the force is being propagated towards like some focal point. Same thing was happening there probably, where it just broke. Definitely with respect to undercurrents too that were flowing. Still no internet. From under Antarctica, through Africa, through Antarctica, and then into eastern Australia. That kind of held like a boundary where it was easiest to break away. I'd imagine. That's kind of my thought. Like it held a base. Below that was more, over here was more free to break. Oh, wrong one. And another collision between southern Zealandia and Hikurangi Plateau. Final plate configuration is same as previous models. Okay. Mechanism to explain the immediate opening of the Tasman Sea following accretion. So this provides a mechanism. I mean, there's some other details he talked about for sure. Okay, so then I watched a second lecture. So that was this one, which I'll link. Then I watched this one, Tilting of the Australian Continent, New Evidence from the Subsidence and Deposition History of the Northern Carnarvon Basin. So this is with respect to this region over here. Wonder what is up. Is the world ending? Every time the internet goes out, I'm like, is it time? Is it time? What if the world is burning around me right now? That would be a pretty good indicator that it was burning around me right now. Like, kind of like a precursor. Oh, the internet's out. What's going on? I don't know. Governments start printing news up. Here's the only information you get now. You guys knew too much. We gotta dumb you down a bit. Just a matter of time. If we let them, at least. So, we discovered a northeastern shift of tectonic subsidence from the early Jurassic to the present. So, subsidence low in red, high in blue. And then I just took a bunch of pictures. Unfortunately, I guess these are tiny, but so let's go through them. High subsidence with inland, a little to the north. This is the Exmouth Plateau, Exmouth, however it's pronounced. 200 to 180, and then 180 to 165. So now we're seeing, red is high subsidence, I guess. Blue is low. So then now we're seeing low subsidence, higher inland, and a shifting of the subsidence as it progresses across time. 145, 132, we even see some kind of like moving blob of subsidence or something like that. Like it's a wave, like here and then there. KT boundary, and then subsidence has a little increase at the KT boundary. And then I don't remember exactly. Let me see if I wrote some stuff down. Let me just kind of read my notes from this one. Exmouth Plateau region, northeastern shift of tectonic subsidence from the early Jurassic to present, 200 to 0. This was interesting. Okay, there's pictures of this, I think, too. Pattern of sediment follows a similar pattern to subsidence. So high sedimentation, I guess, or depth of sediment. Yeah, thickness, sediment thickness. Low in the Exmouth, around 200 to 180. High inland. Still low, getting some high, other high peak in the north. Still no internet, okay. Just checking through these. So these are, sorry, you can watch it, I guess. I'm just looking if there's anything that pops up in my head, nothing particular. So let me just go back again, go through those one more time. These sediment thickness, red is high, blue is low. So I guess like deposition amounts. High deposition in the north and inland. It begins with like right here, like kind of there-ish. Let's look at this animation real quick. Bend is here, so like there. Something around there. High there. I'm just wondering if, like, current goes this way and deposits here first. And I guess there and over that way. Just picturing a current flow coming in, depositing sediment, depositing sediment, depositing sediment, but then it starts to have so much like of a wall that it pushes more current into the Philippines, which then gets underneath the Philippines and adds to like actual deposition at that point, maybe. And then deposits, pretty low amounts after there. And then more in the north up there. Significantly more up there in the north as we approach present. Possibly relating to general like current flows from like currents going this way, cutting through here. Freaking internet, what the? I could probably go restart my router, but I don't want to restart recording and stop recording. I guess it would take me a few seconds to at least get the process rolling. Is this playing? This just stopped. But maybe a current went through this way and through here in the late game. Like the, just a thought. Okay, let's keep going though. I'm not sure if I have a slide that I took a picture of. I was hoping, I definitely do. Let's keep going then. Northeasterly variation of compaction of Barrow Group and Forestier Claystone. Here it is, porosity. So porosity, I wrote down porosity of region changed with time, dropping across time. So we have low porosity here, high porosity there. Percentage dropping across time. Less porous. Less porous, less porous. Almost like it is compacting. Less porous, less porous. But it started very porous. Started very porous, and then got more and more compacted, which also it's got compacted, interestingly, from the outside in, kind of like a drying. Like if there's some mass like Australia that then has another mass adjacent to it, it would kind of dry from the outside in. It gives me that vibe. I know it is in marine settings and things, but maybe it's still like super saturated, so it actually releases water and can be compacted more and become less porous. As it like comes from the earth, is saturated, super saturated, but then like it's in a lower pressure environment and starts to the water that's just being like pressurized inward is able to flow out, and then the actual mass of the material presses down to compact it to basically remove the pores. Something of that nature, kind of like just the fact that it does it from the outside in really gives me that feeling. Subsidence plots along the northeast, southwest, and north-south transects suggest a northeastward tilt from late Cretaceous to present. Unfortunately, these images are pretty unillegible because of the size. I don't know why it takes pictures, screenshots this size sometimes. So let's just go through. I believe it's so hard to remember what was what in this. In short, the continent tilts. So maybe I wrote it down, hopefully. There's a huge anomaly around 70 million in subsidence and sedimentation. Maybe let's find that one, this one. Total subsidence rates, total accumulation, sediment accumulation rates around 70 million. There's this anomaly, this peak. And he says, when Australia began to tilt. Huge anomaly around 70 million in the subsidence and sedimentation when Australia began to tilt. And they picked up that signal in the data. The tilting, and then he said, the tilting has been well documented. I've certainly heard it before. So this concept that the Earth is expanding, that Australia is adjacent to North America, like more like this. I don't have New Zealand in here, but generally like this. And it moves away. But as it does so, it's not just like moving away arbitrarily. It's moving away because there's a current pressing against it. Over here. So my thought, I believe it tilts to the south and like along a northwest to southeast along like axis, like across the continent, it tilts southward, so the north side goes up as it moves initially. So maybe, and this is my thought, like maybe like if something's getting pressed on, maybe it tilts up, but then once it starts to move, it's able to like restabilize and like go back the other way. Like it gets pressed on, it raises, but then it starts moving and kind of goes like the other way into, especially into resistance. Maybe it's running into resistance and like starting to slow down partly by tilting, something of that nature. But yeah, a little sad my internet's not working. Okay, so that is that lecture. Revisiting the breakup evolution of Southeast Australian rifted margin. I'm not sure if there was, if I don't think I really took many pictures of this one. It's interesting, this approach the KT boundary. These are margins along the Southeast Australia, so he's like analyzing this area. And he found, or people have found, the elevation change across like distance towards the coastline, the coastal plain, has a age difference. Like this was 280, this was 270, this was 200, this was 170, 180, this was 130, 140, 150. This was 71, 97, 73. Like it's getting lower and lower, approaching the KT boundary, but not really making it to the KT boundary. Although some of these, like this one particularly, but like, and even this one, 71 plus or minus 28, for instance, are kind of in the KT boundary range. But they seem to be approaching the KT boundary, but then the KT boundary happens, which is when the Earth rapidly expands, and what that does is it forms ocean beds on a scale where all this water that is doing this, that's forming these coastal plains, like etching the margin, basically. That's etching this margin, is able to retreat into the ocean, and then it just stops like at the KT boundary, maybe a little bit in like this where there's already like seemingly some water in there, so it's probably so close to its modern level that it's able to actually reach there. Something for that 37 plus. That one's kind of anomalous, as well as I guess this one. That looks also there, I guess. I don't know. So maybe it like comes back up in that time frame. Like as the ocean floor stops forming, ultimately like slows down. Because it really was like rapidly happening at 66 million. The process slows down. Maybe the water receding into the ocean bed starts to rise enough at that time frame that it actually leaves evidence. Although I don't know what okay, maybe those numbers are not mean fission track length. Oh, that's the fission track length. These are fission track ages. So maybe this is, I'm not interpreting this right, but still the same principle. It's something to do with the retreating of water leading to the stoppage of this process. Some other stuff I'll link this to. Some type of possible enhancement of the process at that time frame of 98 million. I believe I only took one picture of that. This one was ultra low velocity zone in the top asthenosphere, deflects mantle flow around subduction zone. I honestly could not understand her. Like, her accent was very thick. Pardon me, ma'am. It was very thick. I was like really trying, but it's complex subject matter. I think she was Italian. Time scale of events around the Cretaceous Paleogene boundary. As soon as I saw this one, I was like, what are you talking about? KT boundary, you say? Or KPG, whatever the more updated interpretation of or label of is. I just took some pictures. This was interesting. The climate response over here, like at the concept was that the Deccan traps, which was before the Chicxulub, which is not an actual impact, but is part of the Earth's expansion process, breaking the continents apart, which I've talked about in other places, which is evidenced by their non-random distribution. Like, many of them are on the boundary of continents, too many, as well as just like the sheer number of them unaccounted for. I found 15 KT boundary impacts in technical papers, for instance. I mean, certainly some rolled out, but like they just chose one that they liked the best, and that's where we are today. It's not complicated. The other ones just kind of got ignored. Like, there's certainly other ones that are, some that like have been noticed, and some that have squeaked through, like Nader Crater, Shiva Crater, Boltish Crater, Silver Pit Crater, Tin Biter Crater, so many. Just anyway, besides the point. Deccan traps was going off, and so they saw a increase in the temperature in this time frame, but then it decreased while the Deccan traps was going off. I was like, whoa, dude. Not climate response, not what would be expected. Role of Deccan is unclear, because we would expect this huge large igneous province to just continue to like at least hold the temperature at a higher level, maybe stabilize at a higher level, but it goes back down almost as if the Earth was expanding. So like it compensated for it in a way where it, like, the temperature went back down, even in spite of the Deccan traps happening. And mind you, it's rapid. It's way more rapid than we understand it to be. So I thought that was really telling, honestly. Like, we don't see significant climate signal post the KPB, the Cretaceous Paleogene boundary. And then I took some pictures of some lectures on the Philippines. I should probably just stop us here, though. I guess I could read some notes real quick. If I still can't tell. I believe it's this one. Yeah, this one is the Naturalist Plateau. So real quick, I'll just go through my notes on this one and very little notes on this. The Naturalist Plateau in the southwest corner of Australia, which I believed to be where Borneo was, this corner. So if we go back to this slide, or this thing, this animation, like it's this one underneath there, right there, I believe is where Borneo was, this generally, and as well as the like general surroundings of it. I don't know exactly which portions of it were there. But so it formed in the early Cretaceous 136 million, and when this is supposedly when Australia and India broke up. So I guess supposedly it's got a relationship to India rather than Borneo, but that's the interpretation. Lava's intrusive rocks on flanks dated to 132 to 128 million radiometric dating. Volcanic sequence of alternating basaltic flows and volcaniclastic beds, which is interesting. Basaltic, like the ocean floor, and then volcaniclastic, like I guess like volcanic and class, like pieces inside the material. Class are like embedded in a like a pebble in a sandstone or something. So I guess probably something of that nature. I don't actually know what volcaniclastic means exactly. And then after this is Wikipedia, after quote the volcanic eruption. I'm not sure if there was a volcanic eruption there or if it, I don't know, maybe one of the volcanic eruptions, subsided from shelf to bathyled depths in the early Cretaceous, which to me was kind of when the Borneo separated, maybe. Eastern flank gently slopes, others are relatively steep. Steepness maybe would be suggestive of them being more like running into resistance, whatever the current is, like running into the beneath this chunk of land. So if it's like going in underneath it, it's gonna like run into resistance more, like get in somewhat, but then it's gonna run into more and more resistance where it kind of can't go any further. Whereas, and so it'd probably produce more of like a steep slope. Whereas over here on the eastern flank, it has like this gap that is more allowing of like a current through. So maybe a gentler slope on the eastern side, kind of was what I was thinking. And then it's flanked by the Diamantina fracture zone to the south, which is this thing, which right here below, not Borneo, but right there. Which maybe we can see it, this here. Which Borneo admittedly does not align with. I was like, does it align with Borneo? No, not at all. Although maybe this boundary of Borneo right here, it does seem to have some relationship to there, maybe. I don't know. I was kind of intrigued by that aspect. And maybe across. Like, this is probably not perfect, first of all. So there's that to it. Especially, like, I definitely have some space between them over here. So maybe it is a little further to the right. So maybe that aligns pretty well, but the rest of it doesn't. I don't know what to make of it. Also over here, maybe that kind of aligns with this right there, with the boundary of Borneo. I haven't really thought about this region. That's interesting. This little nook is kind of in that area. This is kind of between them. This area is kind of between them. This area is where this is, where like current flows in. So maybe continued in, etched in there. Because essentially current's coming along the western boundary of North America, between North America and Papua New Guinea, and then going along these islands and cutting in to separate them from Australia. So maybe it cuts in here and like etches in there, cuts in here, etches in there, cuts in here and shoves current going this way further into Australia, which that current etches in there and there. Maybe cuts in even here some and across to influence that location. So there's some definitely some relationships, like that little nook thing to this region. I don't know. Maybe even there to this one. And I'm pretty sure these are not exact to size, so I need to maybe adjust this a little bit anyway. Okay. Without internet, I guess I'll just stop it here. Maybe record another one sooner or later. Probably soon. I still have... Oh, wait. Wallaby Plateau. Let me say all I have to say about this one that I have right here. This one. 130 million radiometric dating attributed to large-scale volcanic activity on the oceanic crust. 3 large volcanic complexes, 2 smaller, steeper cone-shaped complexes, and some other things. So there's volcanism here for some reason that's more detectable here than over here. I was kind of thinking that there might be even volcanoes like possibly there's volcanoes in the oceanic plateaus that are detectable like those that then like had the continent above it, that also there's a volcano in the same location above it. I don't know, I didn't look into it that much. What I found at a glance wasn't like that promising, but it's just a thought I had where like a current went through not just the oceanic plateau but also through the crust above. That would be crazy when the island was there. So like replacing it above it shows like, oh, this volcano is actually related to that volcano, and some really cool potential to that, like the innards of a volcano on that scope, or like who knows what would be possible then to kind of parallel. But it was just a fun idea that I was hoping would be readily and easily able to be done, but I did not manage to do that. Then I looked into this region and I've watched a video on this region. I got so many notes. That's what I was saying. It is kind of related. Maybe I should just do this one. Sorry, I know I keep saying I'm done and then I keep going. This one, Spratly Islands region, South China Sea, is composed of horse and half grabens and rotated fault blocks parallel to magnetic anomalies. Magnetic anomalies, mind you, are where current flowed. So, like, maybe reminiscent of what's going on in Iceland right now. Like, there's a current flow, more than likely, traveling along a certain path that is then, like, etching the surface above and making it more thin to a point where it collapses in. along like a fissure path, like Hawaii. So probably something with the Horston Grabens was going on like that over here to make them parallel with the magnetic anomalies of the adjacent oceanic crust over here. Consists of stretched, subsided continental crust. So this is continental crust, not oceanic crust, not like a oceanic plateau. It's a continental crust, more like Zealandia, but of Triassic through Cretaceous strata. So I'm not sure if it's truly continental crust or if it's like over here, like this is continental crust over here, this region, but it's accreted and it's newly formed during the Earth's expansion process. So it might be newly formed during the Earth's expansion process, but still like old enough to be considered continental crust because it got thick enough and other things that made it more like it's continental crust. Earliest period of tectonic stretching of crust is associated with, wait for it, the late Cretaceous and early Oligocene, which I would look up. I think that's not the period afterwards, that's later, but second period of stretching in late Oligocene and early Miocene, additional stretching and block faulting. And then starting in the late Cretaceous, fine-grained, organic-rich marine sediments accumulated in the half-grabens within the dangerous ground region, which is, I guess, some region in the Spratly Islands area here. So it's not the most like whoa one, like the other one's more like fundamentally like an earth process. This one organic rich marine sediments sounds a little more like okay than compared to stretching of the crust kind of thing that happened in the late Cretaceous, but localized regions favorable for accumulation of sediments that might contain oil and gas reserves. So I keep coming across oil and gas. I mean, obviously, most of this research that's not academic and like intent in nature is more oil and gas in intent in nature. So there's a lot of oil and gas research. So even I'll see people talking about their research, and it's real blatantly obvious they just work for an oil company, but they're like interested in the earth. They're like, oh, and there might be some oil here. Does that like keep you interested in me like doing this? Like, they don't care, like, but they're just saying it because it's like a thing that is true, like they understand, but they also it doesn't like drive them for sure. But that's how this research gets done a lot of the time. Whoa. Turned this way, the dragon almost looks like a shoulder and a shoulder. And like a head. Some kind of headdress. Like the Birdman. Like the Birdman. I gotta find it in pictures because I can't use the internet right now, but where is it? Maybe here? Birdman. Like this. Okay, guys. See you next time. Peace out.